Okay, so previous course we already uh, introduced what a definition of the Castilian theory is, right? So, and in this chapter we are gonna focus on how to use this energy method to figure out the deflection, okay, whereas the maximum deflection is by using the energy method, okay. And the first we're gonna introduce these called the dummy load, or we say the fictitious force. So, so you can imagine that it is not the real force. It's not the real load. It's a dummy load. Okay. So the Castilian theory can be used to find a deflection at a point even there is no force applied. Okay. Apply a fictitious force Q at the point and in the direction of the desired deflection. Okay, and set up the equation for total strain energy, including the energy due to the dummy load, and take the derivative of the total strain energy with respect to Q, right? Once the derivative is taken, Q is no longer needed and can be set to 0, right? So what is the dummy load method? It's the deflection or deformation equals to the derivative of the energy with respect to the dummy load. And we set up the Q equals to 0. Okay. Okay, so finding a deflection without finding energy. So for cases requiring integration of strain energy equation, it is more efficient to obtain the deflection directly without finding the strain energy. So the partial derivative is moved inside the integral. Okay, so for example, so for what we already taught previously, the deflection or deformation equals to the derivative of the strain energy with respect to the force. Suppose this member is subjecting to the actual loading, right? Or no, or a different force, right? So we can say the inside is the strain energy, right? The strain energy. Okay, it's the strain energy. Right? It's the strain energy. And we can just move this force inside the integral right here, right? So we move inside the integral, we get the third term like this, right? So the force, the derivative of the force, derivative with respect to F is moved inside the integral, right? Okay, so we can rewrite this third term to the fourth term like this, right? Its denominator will become like this. Right? Just move this to the denominator inside the integral, right? Right? And then finally we can get the derivative, the deformation equals to the integral, right? With the partial derivative inside it. You know what I'm saying? So in this form, we don't have to take this energy part into account, right? So we can directly no, to take the derivative of the moment with respect to the force in this case. Okay, in this case. So derivative can be taken before the integration, okay, simplifying the math, especially helpful with the fictitious force. Okay, so for this method is much more helpful with the dummy load, since it can be set to 0 after derivative is taken. Okay, so the common deflection equation, okay? So in this case, we don't have to take the straight energy into account. Okay, so the deflection, right? When the member is subjecting to the actual loading, can be tension or compression, right? So the integral formation, right? So we take the integration, or take the derivative first, and then integral. Okay, for the torsion, the theta, right? Right, the theta. So we don't have to consider the energy, right? So we just take the derivative of the torque with respect to the moment, and then take the integration, right? M the same for bending, right? For bending, right? The deflection equals to the moment, take the derivative of the moment with respect to F, and then take the integral, right? Okay. So there's one examples here. So use the Castilian theory to determine the deflection of point A and B due to the force F applied at the end of the step shaft as shown in the figure. And the second error moments for the AB and BC are I1 and 2I1 respectively. Okay. Okay. So this question is asked the deflection at point A and B. So the force, the real force is applied at the point A, right? However, for the point B, where is zero force applied. So in this case, we can apply a dummy load Q at point B. Okay, this is a dummy load, it's not real. This Q is not real. Okay, it's not real. So to avoid the need to determine the support reaction force, define the origin of X at the left end of the beam. Okay, so we can define two sections of this beam. One is from 0 to L. And its bending moment equals to minus Fx, right? So right? Right? Okay, so since the F is applied at point A and in direction of the desired deflection, the deflection at point A, we can get the deflection at point A, right? It's the pure bending, right? In this case, it's pure bending, right? It is pure bending. Okay, so we can remember that the derivative is first. The derivative is first, right? So taking the derivative before taking the integral, right? So we can take the derivative of the moment with respect to force first, and then integrate it. Okay, so we can substitute this equation here, right? Right? So the deflection at point A, right? For the first section is from 0 to half L, right? Half L. And this is its moment. This is a derivative of the moment, right? Derivative of the moment. Okay. For the second section, it's from the half of L to L, right? And the moment of inertia becomes 2I1, right? And the derivative of the moment. Okay, derivative of the moment. So we can solve this equation, right? We can just take the integration of two terms, and finally we get the deflection at point 8. Okay, at point 8. Okay. Okay, so now let's focus on the point B, right? We also have to figure out what the deflection at point B is. So we can set up a dummy load Q, okay, which is necessary at that point. And assuming the Q acts down at point B and X is as before, and the moment equation is what? There are two sections, right? From 0 to half L. The moment equals to minus Fx. And the second section is from the half of L to L. And the moment equals to what? The minus Fx minus Q times X minus half, right? Okay. So now we're gonna solve these dummy load questions or the fictitious force questions, right? So in this case, we need to take the derivative of the moment with respect to Q, the dummy load, equals to 0 within the first section, right? Okay, because the moment in the first section, right, X from 0 to half L equals to minus Fx. There's no any terms of Q, right? So take the derivative with respect to Q equals to 0. And for the second section, right, the X from half L to L, right? So we get the minus X minus half L. Okay. Okay, and then we can figure out what the deflection is at point B, right? Also, there are two terms, right? The first section, the X equals from 0 to half L, right? And we already calculate the derivative of the moment with respect to Q at the first section equals to 0, right? And we also find out the derivative of the moment with respect to Q in the second section, right? Second section, right? So the first term will equal to 0. Okay, so finally, we can evaluate the last the integral, right? Given the deflection at point B. Okay, and which is positive sign means that the Q is in the direction. Means that the deflection is in the direction of the dummy load Q, right? So any questions? Okay, so deflection of curved member. So it's not a straight beam, it's a curved member. Okay, so consider the case of a thick and curved member in bending. So there are four strain energies. First is the bending moment, and the second is the actual force. And the third is the bending moment due to the actual force. Okay, since the neutral axis and the centroid axis do not coincide. Okay, and the last one is the transverse shear. Okay, transverse shear. Okay, so suppose we have the curve, thick curve beam, and we have the external force applied to it, right? So if we cut through any point, any cross section, we can cut any cross section, right? So suppose we cut through the cross section, and the force can move to the centroid axis of this cross section, right? And this force can be separated into the actual force, actual direction, and the radial direction. In the radial direction, right? Because the force move, because of the force movement is not along the action line. So the moment created, okay, the moment created, right? Okay, so if the force move along the action line, so the moment will not be create, okay? Okay, so the straight energy due to bending moment M, okay, from the previous, maybe the last week course, right? We already know for the eccentricity, okay, eccentricity of the beam, of the curve beam, right? So what the eccentricity is, the E equals to R minus Rn. Rn is the radius of the neutral axis. Okay, it's the radius of the neutral axis, and R is the radius of this curve beam, Okay, and the second term is the strain energy due to the actual force, right? It's actual force, and it's strain energy. This is its strain energy. Okay. And the third term of the strain energy due to bending moment due to the actual force. Okay, I will explain this later. Okay, maybe you guys confuse what it is. So I'm gonna introduce this later. Okay. Okay, so why the bending moment due to the actual force? Why? Okay, because the neutral axis is not located at the centroid axis. Therefore, there's a eccentricity E between, right, these two axes, right? So can you imagine that, right? And for the bending moment, the bending moment equals to F times R sine theta, right? Right? The bending moment equals R sine theta. However, due to the distance, the actual load, let's go back to the okay, let's go back to this. So there's a bending moment, right? Due to this F, right? Due to this F. Therefore, F time R sine theta, right? This distance equals to R sine theta, right? Okay. So there's the other moment due to the actual load. Okay, because this there's the neutral axis somewhere. So let's go back to this. There's a neutral axis, right? Right here. Okay, this is a neutral axis. So there's a distance eccentricity with the the centroid axis, right? So the F theta, so this neutral axis right here, right? Suppose this is the NA neutral axis, right? So there the other moment due to this eccentricity E. Okay. Okay. Okay, so we say the total moment equals to F times R sine theta minus the F theta times the eccentricity, because the direction of these two moments are different, right? For the moment due to the F, right, it's in this direction, right? And for this moment due to, so for this first term, this direction like this is clockwise. For the second term is, right, it's counterclockwise. Therefore, we use the minus sign here. Okay. So we say the total moment included two, one is from the force F due to the force movement, and the second moment due to the eccentricity. Eccentricity. Therefore, we can just evaluate the moment, the strain energy due to bending. Just plug this total moment right here, right here, right, and the total moment square, right? We can just ignore this term, right? Ignore this term. Okay, because this eccentricity, if this is eccentricity E is small, so we can just ignore, okay, ignore this term. Okay. Okay, so finally we can just this can be ignored, right? This can be ignored, and we can just simply calculate it to figure out the energy of this due to bending, right? So there are two terms. One is from the F, one is from the actual force, F theta. Okay, F theta. Okay. Okay, so the force term of the strain energy is due to the transverse shear from the FR, which is the radial force. Okay, it's the radial force. Okay, it's a radial force. So for this transverse shear, we have to take this modifier factor into account. Depends on the cross-section shape, right? Depends on the cross-section shape. Okay, so we can combine the full energy terms, right? There are two energy due to the moment, right? That's what I mentioned previously, right? One is from the due to the force movement, and the second is from this actual force. Okay. So we have four terms, right? Right. So, and then we can just evaluate the deflection by the Cartesian theory method. Okay, Cartesian method, right? So we can take the derivative of the moment with respect to F, right? And take the derivative of the F theta with respect to F. Okay. So generally, for the thick circular curve beam, okay, which is more appropriately limits of integration, okay, integration. Okay, so this is the summary. Sorry, this is the specific example of the figure. So I already introduced this previous, right? The moment due to the force movement, right? So we can define the derivative of the moment with respect to F, right? Equals to R sine theta, and the F theta is the actual force equals to F times sine theta, right? So then we can just define the derivative of the F theta with respect to F, right? And so on, so on. So we can plug those terms into the strain energy equation, right? Into the deflection, right? Into the deflection. You know what I'm saying? We can plug all those terms into the deflection, okay? The deflection, okay? This term, this term, this term, and this term, okay? Okay, so finally we got the deflection, okay? We get a deflection of the thick curved beam, right? First term, second, third, and fourth, okay? So this is the result of the deflection of the curved beam, okay, of the curved beam. Okay, so if it is not the thick, it is the thin curved member. Say the R over H is greater than 10. This means the eccentricity is small. Okay, in this case, the strain energies can be approximated with regular energy equation with the substitution of R d theta for dx. Okay, R d theta for the dx. As R increases, the bending moment dominates all other terms. Okay, so for the thin curve beam, okay, for the thin curve beam, this energy can be approximated with the regular energy equation with substitution of R theta for dx. And when this radius of the thin curve beam increase, so the bending moment dominates, right? So we don't have to take other terms into account. We don't have to take, say, the actual force, the transverse shear. We don't have to consider those terms. We only have to focus on the bending, okay, the bending. So therefore, say for the thin curve member, bending moment is taken into account. So we only have to consider, well, we only have to take this bending moment component into account, right? So we can evaluate its deflection with the single termed energy terms of the bending, right? Okay, we replace the dx with the r d theta, r d theta. Okay. So I'm gonna end this course here, and the next I'm gonna introduce the buckling. Okay, the buckling effect for a thin and long member. Okay, so how to evaluate whether this thin and long member will be buckled or not. Okay.